So we start with the mechanical properties of concrete. When we say mechanical properties, in general we mean stress-strain relationship. That's the most descriptive measure of mechanical properties. If you think about stress versus strain, which I assume you have plotted curves like this in your materials lab, for concrete it would look something like this. It has some specific characteristics. To start with, the largest value of this curve, that means maximum strength, is called concrete compressive strength. So note that strength and stress need to be distinguished. Stress is what you apply. Strength is how much material provides resistance to load that you apply. You cannot say this is concrete compressive stress. We don't have such a thing, concrete compressive stress. So concrete compressive strength is at the peak. We use variable F prime C historically for this term, F prime C. Why did they decide to go with F prime C and not FC? Historically, FC was used for stress, how much stress you are applying, and then given that stress was FC, they used F prime C as maximum compressive strength. The strain at which the maximum compressive strength occurs is approximately 0.002 to 0.003. We usually assume 0.002. 0.002, as you know, means that if you have a 10-inch tall concrete specimen and apply compression at 0.02 inches, it would crush. Imagine there is 10 inches long, tall, and you apply compression. 0.002 strain times 10 is 0.02, and it would crush. Note that if it crushes at 0.02, let's say you are sitting there and you look at the specimen, you don't notice it. 0.02 is a very small number, a very small movement. There is nothing to notice, and as a result, we consider concrete a brittle materials. A brittle material. The reason it's brittle is not only because this is a small, is more importantly, after the peak, it goes down rather rapidly. The stress-strain relationship goes down. What does it mean? It goes. I mean, you are pressing it, and how could the force go down? How could the stress go down? Let's say you are doing the test. How could you manage to reduce the load? How do you know when to reduce the load? But how do you know? You look at it, you see when it's cracked, you reduce it. It's very difficult if you want to reduce the load. Practically it's impossible. What you do instead, you don't do so-called a force control test. Force controlled test. What does it mean, force control test? That means you are controlling the force. Apply 10 kips, apply 20 kips, apply 25 kips. That's force control. If you do a force control test, you cannot get this one. What you need to do instead, you do a displacement control test. You don't do this. You do a displacement controlled test. What does that mean? You don't say how much force to apply, you say how much move. So you make the system move slowly. Usually this test takes, depending on how fast or slow you do, between 5 to 15 minutes. So you apply the load, the specimen, the two supporting system, they get closer, and if the specimen can take more load, the system would apply more load. If it can take less load, the system would apply less load. If you have noticed, our machine cannot really do that in the basement. I'm not sure you have tried to make a plot like this or not. The machine is not the one that can do it. Whenever we need to do these things, as I mentioned, I look at collapse of a structure. Sometimes we go to buildings and we take samples and we want to test. Two places I have done the test on, one at SGH. SGH has this machine. Usually I've sent one of my students there, they run the test, come back with the results, or we send it out to do the test. It would be nice if we had that machine. So what happens here, some important characteristics of this curve is that at the beginning, it is almost a straight line. When you start the test, the first portion of the curve is almost a straight line, approximately up to 1/2 of f prime c. Up to approximately 1/2 of f prime c, stress-strain relationship is linear. After that, it starts to go with less stiffness. Why does this happen? When you apply compression, at the beginning up to about 1/2 of f prime c, really nothing happens in terms of damage. When you get to about 1/2 of f prime c, micro cracks start to form. Very small cracks. Those formation of micro cracks start to making the structure more flexible. So why does this go off the line? Because micro cracks are forming. As micro cracks become larger and longer, the curve becomes more curved. You get to a point that the somewhere around 80% f prime c or so, that the micro cracks start to get connected. So as they become connected, the weakening becomes even faster. So therefore, the way you want to think about it, at the beginning nothing happens, then micro cracks form, then the micro cracks start to connect. When would the specimen fail? When all the you have a plane of weakness, and then the failure occurs along that line. If you think about a specimen like this, and you apply compression, one mode of failure is a crack like this would form. And then the sliding happens and the specimen would fail. When you get to the peak, and when sliding happens, there is still friction, and there are other sources of resistance, that it does not drop to zero. It gradually goes down, and this is called the descending branch. The descending branch forms. The slope of this curve, not quite this curve, but another curve, which is which is not exactly the initial stiffness, but somewhat different slope, almost as I'm showing, we use to define the modulus of elasticity of concrete. The blue line, if you say what is the slope of that blue line, is the initial modulus of elasticity of concrete. We don't usually use the initial modulus of elasticity. We use somewhat smaller to represent the variation over the nonlinear part. This modulus of elasticity C, based on ACI, can be calculated from (33) WC to the power of 1.5 root of a prime. This is in PSI. This is its pound per cubic foot. So you use the unit weight of concrete in pounds per cubic foot. You use concrete compressive strength in PSI, and this is a relationship that is developed for calculating modulus of elasticity. This modulus of elasticity is for normal weight concrete. If you have lightweight concrete, I put here for normal weight concrete, not lightweight concrete. There is also lightweight concrete that we don't really talk much about, but this equation does not apply to lightweight concrete. In this course, we focus on normal weight concrete. Normal weight concrete approximately has a unit weight of 135 pounds per cubic foot. When we add rebars to concrete, which when it becomes reinforced concrete, when you have buildings made of concrete element, they are reinforced. Reinforcement is heavier. Usually when you look at reinforced concrete, we increase this 135 to a slightly larger number. A round number to remember is, a conservative number is 150. So 150 is a slightly larger than this to be a little bit more conservative and to account for the weight of the rebars. This is just concrete. When you do reinforced concrete, we usually go with a slightly, some people go 140, some 145. I would suggest just think about 150 and you perhaps more easily remember. This relationship is also for normal strength concrete, as opposed to not for high strength concrete. Normal strength concrete, usually we consider a concrete that has compressive strength of 3 to 8 KSI. Larger than 8 KSI, we consider high strength concrete. Usually we don't have like 9 KSI, 10 KSI. Usually if it's not normal strength concrete, then there is a jump. You go up to about 11, 12 or more strength because you change the way you construct, and that really changes suddenly the strength of concrete. In this course, we work on normal strength concrete and normal weight concrete, which almost, in many cases, those are what we use. In few cases, we might use lightweight concrete. Lightweight concrete several decades ago was starting to pick up, but for different reasons, it didn't really work out and people didn't use much. Nowadays, rarely people use lightweight, but seems to be there is a trend that people are starting to use lightweight again, not much yet. Higher strength concrete, however, is becoming more in use, particularly when you look at tall buildings, very tall buildings. Then a concrete strength of 8 really doesn't do it. They go up somewhere around up to 20, even higher. So 20 KSI concrete compressive strength is really high, and they can manage to do that, and as a result, that tallest building in the Middle East is made of high strength concrete, and I guess the concrete strength, I'm not quite sure, was in the neighborhood of, I guess, 16 KSI. Okay. So, any questions so far? Okay. We talked about concrete compressive strength. Now let's a little bit talk about concrete tensile strength. Or maybe before going to concrete tensile strength, let me talk about concrete samples. The sample size that you used in your materials course was, I believe, 3 by 6. The cylinders are, again, historically are proportion to a 2 by 1 ratio. The height to the diameter is a 2 to 1 ratio. 6 by 3 is used because you don't use too much concrete, is smaller and you can manage it better. But 3 by 6 sample is not a standard sample. In the industry, you cannot use this one. The standard sample is a 6 by 12. So this is the standard sample, much larger and heavier. It takes some effort to carry it. This is the standard sample, 6 inches by 12 inches. And the same idea that this is a little bit maybe too big. The industry was trying to make it smaller. Recently, in the maybe a decade or so, a 4 by 8 has become also an acceptable sample size in the industry. Not many people many people still in the industry rather to go with 6 by 12. They have been doing that forever, they're just continuing that. But some people go to 4 by 8. 3 by 6, again, is not standard. You cannot use it for actual projects. When you pour concrete, obviously you take samples to make sure the quality of concrete is good, and then you keep sampling based on the amount of concrete and based on the time that you do and other factors. When you report F prime C is always average of 2 tests. You don't do just one test and report it. Whenever you say f prime c is 4 ksi, that means I did 2 tests and the average of the 2 was 4 ksi. If you are going to the smaller sample, it has been understood that the randomness of the characteristics becomes higher. That's why the code says if you use 4 by 8, you need to find the average of 3 samples. This is average of 2 samples. This is what is used in the US. In Europe, they don't go with cylinders, they go with cubes. The standard cube size is 15 by 15, that's in centimeters, 6 by 6 by 6. Of course, it's not really 6 by 6 by 6, it's 150 by 150 by 150 millimeters, because in Europe they don't use inches, but approximately 6 by 6 by 6 is a kind of half a standard is 4 by 4 by 4. And there are relationships between, let's say, someone from the US wants to study a building in Europe, and they have samples in terms of cubic samples. You cannot just directly say, okay, I assume cylinder is the same. People have developed over time relationships, how to convert them. There are different curves, different ways of converting them, but that's not really our issue. We just look at those cylinders. When you do the compression, before we go to the tension, when you do the compression, when you see this, is better to, instead of saying concrete is cracking, it's better to say concrete is crushing. You can't say, obviously, I see a crack, because that looks like a crack. But given that it's in compression, it's better to describe it that is a crushing is happening, and reserve cracking for tension. So we say concrete in tension would crack, in compression would crush. So now let's go to tensile strength. Did you do any tensile strength test in your materials lab? You did. How did you do that? Anyone remembers?
We used, I think it was like cylinders of plastic. And
We want to find the tensile strength of concrete.
I did the 3-point bend-in.
Where? Here?
Yes.
In the basement?
Yes.
When?
Last semester.
Oh, yeah. Did anybody else did 3-point bending? Okay, so you know what it is. Okay. So how about sideways cylinder crushing or cracking? So there are 2 tests that you can do. One is splitting. Tension test. This is an easier test to conduct. The reason it's easier is you use the same type of cylinders that you use for compression. You use the same thing to do tensile test. Before I continue, so I sent this sign-up sheet. Please put in front of only your name. Just initialize it. A splitting tension test is you put your cylinder sideways, and then there are some requirements as to you put a piece of wood here, a piece of wood or something similar here, and then you apply compression. Interestingly enough, when you do a specimen like this in compression, that sample is almost always cracks like this. This is cracking, not crushing. That crack makes two half cylinders. That's why it's called splitting tension test. You do this, the concrete splits to two halves. There are different ways of explaining why this happens. One way, based on your knowledge of statics, if you apply compression like this, at the top and very bottom you have small area. As you get to the center, you have a larger area, obviously. The way you can think about it, because you have larger area, you can think that on average the load is transferred through these concrete compressive struts. If you think about your static course, is this system of loading in equilibrium? Think about your truss. You analyze truss structures, different methods. One was looking at equilibrium of nodes. Is this in equilibrium? Is this node in equilibrium? The top force is pushing out, the bottom force is also pushing out. If you look at the horizontal direction, both of them have horizontal component outwards. The only way you can satisfy equilibrium is if you pull them in. That pulling in, that material in the middle, in order to pull in, the materials would go under tension. And that's why simple way to think about why tension would develop in the middle. So the load wants to transfer that way to bring it back in. This is kind of a simplistic description of what happens. A more accurate evaluation is there is a course called Theory of Elasticity. What is the course? What is that? This is usually a graduate course. What it talks about is in two-dimensional space or three-dimensional space, how stress and strains develop under different boundary conditions. When you analyze this using theory of elasticity, you would see that your analysis show this variation of stress over the height of the specimen. What does it represent? At any location, the horizontal distance between this vertical line and the curve shows how much tension or compression you have in the horizontal direction. this would show that for the most part you have kind of uniform tension. Only at the very top and very bottom you have compression. So these are two ways of describing why this happens, but that is called, again, splitting tension test. And when you run this test, the force that you calculate or you find that causes splitting, let's say force P, if you use 2P divided by pi L D, 2P, 2 times the load applied, divided by pi, 3.14. L is the length of the cylinder, D is the diameter of the cylinder. So if you do this, this calculation, you find tensile strength of concrete. This really again comes from the theory of elasticity. In reality, however, rarely we have a specimen that is under this condition. You don't make a concrete and put up sideways and apply compression. This is a good test. Easy test. Why easy? Because you use the same cylinders that you use for compression. You just make a few more and test it. A better test that would represent more realistically beams and columns is what you mentioned that you ran the test on, which was the beam test. So you make your another sample. Now this is rather long and a different geometry. Why is it a different geometry, or why is it more difficult? Because you need to have formwork for this and make them. Okay, if it was just cylinders, you just make 2 more cylinders. But here you are talking about a different geometry. The cross section of this cylinder, the standard size, is 6 by 6. When you run the test, from the center of support to the center of the support, it's going to be 18 inches. That means 3 times 6. So you have 18 inches, and then you apply the loads . 6 inches apart and symmetric from the center line. So 6, 6, and 6. So after you run the test and the specimen breaks, we discussed that before, that it would break under tension and due to bending. As a result of bending, tension would occur at the bottom of the beam and it would break. Where do you think this beam would break or the first crack would fall? Bottom, and where?
Normally center.
Center. Is that, do we all agree that this will be at the center of the beam? Why would be the center?
Well, I'm not sure. This one's like 4 points, right?
So this is the way you run the test.
The one I did was 3.
With 3. This is usually to run the test.
Well, everything's symmetric, so.
Okay. So then the center would break. So is that convincing enough? I mean, we say everything symmetric, therefore center. If I say, what about here? What about, let's say, here? Not center, slightly to the right or slightly to the left. Can it crack from there? How do we make that judgment technically?
We have to check for where the highest tensile strength is.
And where is the highest tensile stress?
Supposed to be in the middle.
Middle of the beam. But why the middle? I mean, if I say slightly to the right or left, what would you say? Say no?
Is it where moments maximum?
So you need to think about it technically. Why does it break? Because of the moment. Where does it break at? Where the moment is maximum. Is the moment maximum at midspan? It is, but it's not just the midspan that has maximum moment.
It's anywhere in between the two.
Exactly. So if you look at the moment diagram of this beam, it looks like this. So anywhere between the two loads, it can break. In fact, in reality, it could even break outside of those two loads. How do you think that could happen?
Like issues with the concrete mix, design the concrete mixture,
Meaning what?
just inconsistencies, like errors.
Correct? So if there is some flaws, let's say somewhere, let's say there is a flaw here, moment might be slightly less, but that flaw may lead to cracking. Usually we say that if the specimen didn't break between the two loads, we disregard the test. So we run the test again. We did, a few years ago, I don't remember, maybe 6 of these tests, 1 of them broke outside the range. The other 5 cracked in between. So when you run this test, how can you get the concrete tensile strength from the test? Did you calculate it? How did you do that?
It's a little longer, you have to like, once you get the maximum,
So you'd first need maximum moment. What is the maximum moment?
the actual test will show you where the maximum is.
But let's say we want to do it here based on our knowledge of statics. If you have a beam with load applied at P with this geometry, what is the maximum moment? I suspect some of you know, but this is a measure of your how fresh you are in statics. So the expectation is you need to maybe refresh your memories so that a question like this, when I ask, you immediately answer. So now who wants to answer? What is it? What's the procedure? What do you need to do? We don't need to memorize these things. You need to find. How do we find? How do you draw the moment diagram? So you want one way is to draw the shear diagram first and then draw the moment diagram. That's the standard approach. We can just skip that part as well. I explain in a moment. But how does the shear diagram look like here? Do you do anything before drawing the shear diagram? You first calculate reactions, right? So what are the reactions here? And how much are they? P and P, correct. To have 2 P's, each one would be 1 P. Okay, there is really no need to do the real equation. You're just looking at it, you know that reactions are P and P. if you want to think about it without a shear diagram, can you, just by looking at it, conclude how much moment we have here? Want to guess?
Calculate the area?
With what you see on the board, can you just prove or make a statement as to what the moment is there?
Is it PL over 3?
Based on what you see there, what did you want to say? No. Why the moment here is this reaction times this distance? Correct? So that's what you said, PL over 3 based on this. So what we have here is this length is 6 inches, which is L divided by 3, PL over 3. Okay? Consider this. If you know this, the better. If it's not clear to you, that's kind of a the lowest bar of statics. We will need much more than this knowledge of statics, fresh, that you can use and solve problems. So, therefore, the maximum moment in this case, if this is 6 inches, would be 6p. What we did so far falls under the topic or the subject of statics. Statics stops here. What is the outcome of an analysis in statics? You find support reactions, you find internal forces, and if it was needed, you calculate deflections. In this case, we are not asking for deflections. So the static is finished. How do we calculate the tensile strength of concrete now? And based on what, how are you thinking about moment of inertia? Okay, and how do you want to use the moment of inertia?
Determine the stress at the bottom of
And how would it be related to the moment of inertia?
I'm not sure.
So let's talk about it in a general term first. What is that 6p if you want to describe it the most technical way other than maximum moment? What measure is that we are using? We said when we design and we look at evaluation of a system, what we need is internal forces. That drawing shows the internal force applied to that beam. When we say force, we use that term rather loosely. We consider moment also as a force. In physics, if you in your physics exam write moment is force, you may lose some points. But in this case, you can think about moment as a force because that's an internal force. If we have the internal force and we want to calculate the stress to relate to the tensile characteristics of concrete, we need to have a relationship. This is the global way to think about it. A relationship that relates stress to internal force. This could have many different forms depending on what you are looking at. So we'll need to look for internal force stress relationship. In general, any problem under any loading condition, you would need to find internal force stress relationship. That's the science that comes to play. and say, how are they related? What is the science that covers this? What's the title of that subject? We talked about it last time. Solid mechanics or strengths of materials. If you open a book called Strengths of Material or another book called Solid Mechanics, these are types of things they talk about. If you have moment, what would happen? If you have torsion, what would happen? If you have shear, what would happen? So one of the important topics there is being able to, when you do this, when you relate internal force to a stress, you are analyzing a section. What section? In this case, a section that would be somewhere between these two, which looks like this. So in general, you need to have these relationships for different loads and different sections. For in this case, what we are talking about now, what type of internal force are we talking about now? Moment. Don't forget. You don't just think about internal force. You have to be specific. At this time, we are looking at moment. Later, instead of moment, we look at shear. We develop a different procedure. Okay? If you have an element under compression, it's a different case. You need a different internal force stress relationship. So what is the stress internal force relationship for a rectangular section under moment?
Stress is equal to my rho.
Say it again.
Stress is equal to my rho.
Stress is equal to my over I. What is y?
The distance from axis to the or whatever distance where you.
Correct. So depending on where you are calculating the stress, let's say you want to calculate the stress here. Anywhere that you want to calculate, you need to find the neutral axis which passes through the centroid of the section. This distance is y. I is the moment of inertia of the section. Have you seen how this relationship developed? I don't know if it's covered in solid mechanics or not. Did you see why do we have this relationship? No. So you can develop this relation. Obviously people have developed it. You can see that an integral appears that would represent moment of inertia. But let's skip that part. So this is kind of a very interesting relationship. Just think about it, what terms are appearing. Stress, we are obviously looking for. Moment is the internal force. How do you describe, if you want to use a general term that would describe both y and I? What are they? Do they depend on material properties? No. What do they depend on? Or in general, geometry. They have nothing to do with material properties. If you make this beam out of concrete, steel, wood, or whatever, y and I don't change. So that's also important to recognize. These two are geometric characteristics. For instance, when it comes to moment, or let me ask you this, what other geometric characteristic than I do you know for a section? If I give you a section, I ask you, give me some geometric characteristics. Area. Area is enough. When do we use area? Under what load? Tension or compression? Axial force. You can see that when it goes from moment, you go to axial force, moment of inertia changes to area. Now, I'm not sure you have seen this. What about shear stress and shear force? Anyone remembers the relationship between those two? So we will look at that later, but for now, what I wanted to point out was that a section has different geometric characteristics. Depending of internal force, you may use one or another. And how do you know which one to use? That's the science. You solve, you start the process, you develop a differential equation and solve it, and you get to this point. So, what do? We find the force, we find the maximum moment, and we say, okay, that was as much as statics was helping me. And then we say, okay, what can solid mechanics do? Solid mechanics gives you this. You relate them, and you find your stress. That stress is called modulus of rupture. It's kind of unusual term for tensile strength, I think. But the reason I believe they used it was tensile strength was already used. People were doing this test, and then the other test was developed. The alternative term they used, modulus of rupture. Usually, modulus of rupture is a better measure of tensile strength that we use in evaluations. Roughly, modulus of rupture is 10% larger than tensile strength. Roughly. It's not a perfect relationship, approximately 10% larger. Modulus of rupture, if you want to calculate it more accurately, and you have not done the test, of course you can do this test and find it. If you have not done the test, the code says you can also use 7.5 root of f prime c. 7.5 root of f prime c. In ACI, whenever you see f prime c, you will use PSI, not KSI. You cannot use KSI here because this relationship is not a linear relationship. Therefore, it's unit dependent. So always you would use PSI. So you use PSI and you calculate it. This gives you a tensile strength approximately 10% of f prime c. Of course, you can do a more accurate, just calculate it and see what you get. Sometimes a little bit less, sometimes a little bit more. So you can use this one to calculate the tensile strength. F of t is approximately 6.7 root of f prime c. Questions? Okay, what?
So in the beam test we use modulus of rupture?
Not in beam test we use, modulus of rupture is used. Beam test is used to calculate modulus of rupture. If you want to maybe rephrase your statement is, now that we found the modulus of rupture, in reality, if I want to look at tensile strength, which one do I use? I usually use f of r, not f of t. Any other questions? Okay, why don't we take a 5-minute break and then we'll continue. Where is the sign-up sheet?
My name is not there in here.
Could you add your name then at the end? Why you added later?
Yeah.
Okay.
No,
have a
of this
Oh, sorry. 6.7, that's the,
f of t,
that's to get f of t, which is tensile.
tensile stress. This is f of r, not tensile stress, tensile strength.
Tensile strength. And this
This is modulus of rupture,
FR,
f of r. Both are measure of tensile strength. Okay, thanks.
Y ahí cómo se cerra.
For the bending, the stress is different from the different point of the beam, right? Like at the bottom is the most.
Yeah, wherever you calculate y from, that would be give you the stress. If you use the y for this point, that gives you the stress here. If you use y this for this point, that would give you the stress there.
Okay.
¿saben qué? La tensile-
Es el tangent. Yo creo que
What is it?
delta, that delta t, is that delta t?
Delta t where?
At the corner right.
You are talking about this. This is f of t. This is the same f of t.
No sé, creo que ahorita me dice que Rodolfo preguntó y lo dejan ver. Pero no sé
Es muy chill, te lo digo. Toda la gente, mira, yo conseguí, o sea, yo me hice amigo con mucha gente ahí, todas son panas. Si tú puedes pagar, but it was just like, it was, yeah. I really got frustrated. Ellos son mayores, o sea, es mayor, por ejemplo, mañana voy cualquier cosa a él y él. Sí, no sé qué.
como que me dijeron que
Yeah, I'll have you sing it. And that was definitely You win the fall.
y después yo le iba a preguntar a una niña. No, pero también que me hubiera entonces le iba a preguntar a una niña que
No le pregunto a nadie. No,
O sea, era buenísimo porque era súper barato. Sí, eso es lo que quiero preguntar. ¿No te sabes
No, ni siquiera. Ellos van a construir una oficina temporal.
O sea,
Olvídate de...
You went yesterday for the seismic
In Boston, Massachusetts, a seismic building code.
well. And
They want to update the code.
so like how do they want to update it?
It was more about how to get public be aware of earthquake in this area that they don't have much earthquakes.
I thought there weren't a lot of earthquakes around here though.
There is none, but there has been earthquakes in the past.
Okay.
In 1755, there was an earthquake magnitude about 6.3.
That's big.
So about 50 miles away.
Are buildings like ready for an earthquake right now?
Yes, after the building, I had a presentation that the conclusion was building constructed after 1975. They are in good shape. The one that before, some of them are questionable.
Makes sense. Because they didn't.
Consider the code, correct. Okay, why don't we continue? I noticed one equation I forgot to give you is that E of C can be approximately calculated as 57,000 of root of f prime c. That's an approximation to the previous equation. I gave you 33 wc to the power of 1.5 times root of f prime c. This is, if let's say your concrete is 135 pounds per cubic foot. So this is an approximation. Usually many engineers just use this one. But if you are concerned about unit weight is smaller, you may want to use the other equation. So in this course, when you are calculating the modulus of elasticity of concrete, you can just use this equation and find it. Note that modulus of elasticity of concrete depends on the tensile strength. The higher the tensile strength, the larger the modulus of elasticity. Any questions before I move on to steel mechanical characteristics? Okay. So let me maybe bring up some bigger picture type of thing. You make samples of concrete, either cylindrical or this cubic, and go to the lab and test them. What you find is stress-strain relationship. You then use the knowledge of statics to find internal forces. Then you relate the lab test results, knowledge of statics through solid mechanics to do design. So that's why statics and solid mechanics are a pre-requirement for this course. We use not only the static part to do structural analysis and find internal forces, but also the solid mechanic different parts of it that would relate internal forces to stresses and other types of relationships. Being able to analyze structures, as I mentioned before, is a must for design. If you cannot analyze the structure, there is nothing to design. I mean, if you say, design a beam for me, nobody can design such a beam. Beam to do what? Okay. So when you want to design a beam, let's say you want to design a beam of this building, you go through some process to get the bending moment diagram of that beam. That's called analysis. You have material properties based on this, steel, concrete, and any other types of materials you are using. Then having those two pieces, the tie happens through solid mechanics. So the combination of those all are needed. That's why you take the course materials, you take statics, and then you are taking concrete. And of course, many of you have taken structural analysis, some of you haven't. So as a side note, not that again is required, but structural analysis and statics, what's the difference? What's common, what's different?
Well, different. In structural analysis, you learn how to solve for statically indeterminate structures, whereas statics is just determinate structures.
What's the difference between statically determinate and statically indeterminate structures?
You can solve for the reaction forces just using like a truss, for example.
Can you use more general description?
The amount of equations you have is equal to the number of unknowns.
That's correct, but a little bit more specific. Let me just tell you what I mean by more specific. When you analyze a structure, the number of equations have to be, regardless of any other consideration, equal to the number of unknowns. Can anyone say why? Statically determinate, statically indeterminate, whatever you want to analyze. The number of equations are exactly, not more, not less, exactly equal to the number of unknowns. Mathematics is needed now to answer this question. You have taken this course in mathematics. What's the name of the course? Differential equations. Part of that is, I assume you to discuss the system of linear equations. What do you know about system of linear equations? If the number of equations and number of unknowns are equal, then what? There is unique solution. Why did I say for a structure they are always equal? How do we know there is a unique solution?
Because the load and the number can be two different things at the same time.
Maybe because there is no proof for it, but maybe all of us agree that if you maintain everything the same, if you run a test today or tomorrow, you don't expect to see different results. Of course, things could change, temperature could change, or other changes may happen. But as long as things are the same, we have this understanding that things should not just change. Therefore, there are unique solutions. Can we find them is a different question. But the number of equations and number of unknowns are always exactly equal. Cannot be one more or one less. The only question is, what types of equation are we talking about? So what type of equation did you describe when you look at statically determinate structures?
Global equilibrium.
Or general equilibrium equations. So when you are looking at knowledge, the subject of statics, the type of equations you are using is of equilibrium type. If the structure is statically determinate, as long as you use equilibrium equations, you can solve the problem. What happens to statically indeterminate structures? What other types of equations do you use? Compatibility equations. So I know a few of you have not taken structural analysis, just as I'm trying to touch on that a little bit. This beam, is it statically determinate or indeterminate? How do we know? Proof.
When we did structural analysis, we used an equation that said if there's so there's 3 unknowns here from the fixed end,
There are 3 unknowns, correct?
and then we just minus 3 from however much unknowns.
So
we have.
where is the other 3 that you will minus it from?
Usually we just minus 3 anyway.
Okay. Now if you want to understand that, what would that be?
So here there's 0 because there's
That's correct. But you are correct that you say 3 minus 3 is 0. One of these 3 is this 3.
yeah,
What is the other 3?
the equations for it.
What does it mean, equations?
So there's an equation for the moment, there's an equation for the axial force.
Vertical force, because doesn't need to be axial, could be at some angle. So you have some of the forces in the vertical direction equal to 0, some of the forces in the horizontal direction equal to 0, and some of the moments are equal to 0. So as perhaps you were trying to say is that you have 3 equations, 3 unknowns, 3, if you want to be more specific, equilibrium equations. You have 3 equilibrium equations. So if I say you have 3 equilibrium equations, that is not technically completely correct. You have to be even a little bit more specific. What do I need to say to make it more specific and correct? Do I always have just 3 equations? Is there a case that I have 6 equations? How do you want to correct that statement? That 3 equations is exactly correct. In 2D, 3 equations is correct. That means as long as the structure is on one plane, you have 3 equilibrium equations. If you are looking at the 3-dimensional space, you have 6 equations. So that 3 is not really exactly correct. You have to be specialize it. In 2D problems, for systems that are rigid, you have 3 equilibrium equations. If now I add this support, now the structure is statically indeterminate because we have still the 3 equations, but we have 4 unknowns, correct? So if you have 4 unknowns and 3 equations, what can you say about that system based on mathematics? Those mathematics you read every now and then are useful. Perhaps the most useful, if you wanted to refresh your memory on mathematics in general, if you want to become a better structural engineer, the part of mathematics that's mostly used is the system of linear equations. I teach advanced structural analysis, we keep using system of linear equations. So that's a part that is useful. But if you have 2 equations, 1 unknown, what can you say about it?
Is it a DSI of 1?
Forget about structures, mathematics. Or if I have one equation, two unknowns. I could have three equations, three unknowns. We discussed that. Then you have unique solutions. If you have now one equation, two unknowns,
No solution.
or
Set of solutions.
or infinite solutions. What does that mean? X plus y 5. If you want to describe it, is one equation and has two unknowns. What if I say find the value of x? You can say I have infinite values. What do you want? How do those infinite values form? They form a line. This equation is equation of a line. Any point on that line is correct. So if the number of equations are less than the number of unknowns, then you have infinite solutions. Correct? Everybody agrees? Now in this case, after adding that support, the number of equations is 3, the number of unknowns is 4. Conclusion? From a mathematical point of view, if that is the statement of the problem, we have infinite solutions. Everybody's on board so far? Okay. So, now let's go to structures. Does it make sense to say this structure now has infinite solutions? No, we know by on general understanding. This is kind of philosophy. We know that's the case. Okay, we know that this system has a unique solution. If I apply a load here, a specific load, we expect to have unique solutions. Therefore, what? There must be one more equation. Not 2, not 3, not 0. Exactly one more equation. And that equation is of what type? Compatibility type. So just going through the process one more time. If the number of equations are less than the number of unknowns in a structure, you would know that exactly the difference of those two is the number of compatibility equation you have. There is no way to have one more. If you had one more, what would happen? If you had two equations, one unknown, what would happen?
Wouldn't it be unique?
Not unique, not infinite, something else. No solutions. For instance, if I say this as simple as this, x is equal to 5. How many equations, how many unknown? One equation, one unknown. I want to add another equation with the same unknown. X is equal to 6. I have two equations, one unknown. What's the answer? It's impossible. We cannot have x5 and 6. So if you have two equations, in this case, now if you have three equations and two unknowns, with the same logic, you say it's impossible. You cannot satisfy three equations in general with two unknowns. There needs to have one more unknown. Okay, so that's kind of a wrapping up of this. So let's now briefly talk about reinforcement. How many of you have seen reinforcing bars? Okay, how would you describe it? Round. What else?
Rigid, circular rigid.
So what it has is not smooth. It has these things, we call it deformed. bar. Deformed, that means there are that surface deformations intentionally developed. As opposed to, we are not talking about reinforcement, as opposed to round bars. This is round, this is deformed. For several decades, ACI does not allow the use of round bars. You need to use deformed bars. And the reason for that is we are using it in reinforced concrete. We have reinforcement and concrete. A deformed bar provides a much better bond between concrete and rebars. Much stronger mechanical bond. Therefore, we don't use round bars, we just use deformed bars. Deformed bars in the US have numbers the size of deformed bars are from 3 to 18. Let's say number 3, which is the smallest bar. The diameter of number 3 is 3/8 of an inch. Up to number 8, the diameter of the bar, could you just speed up the process a little bit? So the diameter of the bar is the bar's number divided by 8, up to number 8. That means if I say what's the size of number 8, the diameter of number 8 is 8 divided by 8 is 1 inch. So the diameter of number 8 bar is 1 inch. However, the diameter of number 9 bar is not exactly 9 divided by 8. Starting number 9, there is a slight variation, and the reason for the variation is that to have a better number for for area. For instance, what is 9 divided by 8 is 1.125, right? If you look at the diameter of number 9, how much is it, the last column? So slightly different, but the reason is if you use 1.128, the area becomes round 1. That's why they changed the diameter slightly to find better numbers. Now the diameter of number 10, instead of being 1.25, is 1.27. If you do that, you get a nice number, 1.27, 1.27. So that is in general. So you would use this to find the area of the bars. Usually we don't use diameter, we use diameter later. But at the beginning of the course, the only thing you need is the areas. So bar, after you solve some problems, you kind of memorize it. So number 8 is 0.79, number 6 is 0.44, and so on. So this is the table that gives us the area of the bars. Reinforced or reinforcing bars, or short rebars. Reinforcing bars, usually in the industry, is known as rebar. We abbreviate it to rebar. The stress-strain relationship for reinforcing bars is something like this. The modulus of elasticity is approximately 29,000 KSI and is constant, unlike concrete, is constant regarding the strength of rebar. If the strength is 40 KSI, 60 KSI, or any other number, the modulus of elasticity of rebars do not change. The point at which yielding occurs is called yield stress, F of y. The yield stress is also known as bar's grade, the grade of the bar. If the yield stress is 60 ksi, which is more often used, we say this is bar grade 60. We have grade 75, we have grade 100, we have grade 40. 60 is more often used. There is a movement towards having a larger yield stress because you can have a better design. But 60 is the one that is more often used. The strain at which F yield happens is Fy divided by 29,000. That is called epsilon yield. Concrete does not yield. We don't say for concrete that strain that we showed was yielding. Steel rebars do yield. That's yielding. If Fy is 60 ksi, epsilon yield is approximately 0.002. It's interesting that this number happened to be equal to the strain at which concrete has maximum strength. Just happened to be. Again, this is for this point. This point is epsilon at rupture. Epsilon at rupture could be as approximately 0.1 to 0.15. How many times is 0.1 larger than 0.002? 50 times 0.002 becomes 0.1. So this strain is 50 times larger than the strain that you have here. That means if a rebar starts to yield, in order to get to that point, it needs to yield deformed 50 times more. That's a lot. That's why we say rebars are ductile, as opposed to concrete that was brittle. Concrete is brittle, rebar is ductile. If you have a 10-inch long rebar and you pull it, at what length do you get to 0.1 strain? 11. So your 10-inch bar becomes 11 inches, still is not broken. You can easily see that. But concrete, on the other hand, if you did the same test, it would move by 0.02 inches, and you cannot even notice. Okay? So concrete is brittle, rebar is ductile. The interesting science of reinforced concrete is that if you combine the two effectively, you can make a reinforced concrete that is very ductile. Okay, so on Saturday I was thinking, this winter I didn't catch cold. On Sunday I started coughing and it doesn't stop. So here what we have is again rebar is ductile, concrete is brittle. The science of reinforced concrete is to make them such that when you combine them to have a ductile element. Why ductile is better than brittle?
Because you can foresee the failure before it.
Exactly. So it can give you warnings if things wants to fail. If an element is deforming very little, you cannot notice, you don't see anything. But if you have a beam that is sagging 1 foot, you know something is wrong here, right? So that's why we want to have a ductile behavior. And let's just stop here. We reconvene in 12 minutes or so. I'll be back in 10 to 12 minutes. You are done. The next class doesn't need recording.
Yeah, actually I had another class.
I see. Okay, thank you very much. I'll see you.
Have the mic.
Oh, yes. Glad you were here because I was going to my office. So the other. Thanks again.